In this part of 5.4, we're going to be looking at modeling and optimization problems for economics. So we're mostly going to be looking at profit, cost, and revenue. So the first part is looking at profit. Now, if you remember, profit would be equal to our revenue minus our cost. And so another way of looking at maximizing profit, notice that if I took the derivative of my profit, I can think of this as r prime minus c prime. And if I want to maximize, this is going to be where r prime minus c prime is equal to 0. Okay, we just set that equal to 0. Notice this is going to happen where our marginal revenue is equal to our marginal cost. So a shortcut for finding maximum profit would be looking at where these are equal rather than just finding this equation first. Okay, another way of looking at this then is graphically. We want to be careful though, because notice we might get those zeros where these two things are equal to each other in a couple places. If it's happening when the cost is greater, this is actually going to give us a loss here. Whereas if the revenue is greater than the cost, it's going to give us a profit. So we're looking where our tangent lines are parallel to each other, but we want to make sure we're getting a profit. And when they're the same, that's going to be our maximum profit. So in this problem, maximizing the profit, we want to start by, since they've given us the revenue and the cost, looking at the derivative of our revenue, which is 9, the marginal cost, or derivative of the cost, which is 3x squared minus 12x plus 15. And so to maximize our profit, we're going to set these equal to each other. Dividing by 3, we'll get x squared minus 4x plus 2. Notice we can't factor this, but using our calculator we'll find these values at 0.586 and 3.414. Now we need to decide which of these would actually be the maximum profit. We would probably take that, we could plug back into our original functions, find where the revenue is larger. We also have a graph here, so notice the blue one is our cost function. This lower value then, the cost is greater, this is actually a loss. So this would be our profit over here, and so that's actually going to be our maximum value. To answer this then, this is going to be our maximum when 3.414, look at your units here, so 3.414 thousand units are produced. The next part is minimizing average cost, and the key here is average cost. When we're minimizing average cost, this is what we're trying to minimize. Our cost function divided by the number of units produced. So what we're really looking for is the derivative of this. So if we're looking for the derivative of our cost divided by x, we would need to use the quotient rule to actually work that out. And if we solve that, move everything over, we end up with the marginal cost, c prime of x, equal to c of x over x. Okay, because we're getting our derivative of cost here, and that is actually our marginal cost. So as a shortcut to this, we're just going to take the derivative of our cost function and set it equal to our cost function divided by the number of units. So in this problem, we're given a cost function. We're asked to minimize the average cost. Not minimize the cost, but the average cost, the cost per unit. So if we look at our cost and find the marginal cost, so the derivative there, and then take the average cost, we take this function and divide it by x, which gives us x squared minus 6x plus 15. To minimize this then, we're going to set these equal to each other. It gives us 2x squared minus 6x equals 0. We can simplify that to 2x times x minus 3, giving us x's of 0 and 3. Now we need to decide which of those would actually make sense. If we're thinking about a production level, we don't want to have a production level of 0. So we're thinking that x has to be greater than 0, so we're going to ignore that. The only possibility really is x equals 3. We do want to check though to make sure that that is a minimum value. One way to do that is looking at the second derivative. So if I think about the derivative, remember we're maximizing average cost. So the derivative of the average cost would be thinking that as cx over x, and that derivative would be 2x minus 6. Our second derivative would be 2. We notice that that second derivative is always positive. telling us that we're concave up, and since we're getting that 0 at 3, we know that this has to be a minimum value. So is there a production level that minimizes average cost? Yes. What is it? It's x equals 3,000 units, taking that 1,000 from right here. Now notice also that really with this one, this average cost function was pretty simple to work with. We could have just taken this derivative and set it equal to 0. But this method does give us tools when our functions are a little bit more complicated.